Okay, I'm just seeing three of us. Would that be, where are the others?
I can't say, sir. Maybe they are busy.
Okay, let's shoot. So good afternoon. If you can hear me, kindly reply with good afternoon.
Yes, sir. Good afternoon, sir.
Okay, good. All right. So I figure we're supposed to have this session yesterday. So sorry we are just having it today, like a makeshift class, or should I say impromptu. And also I'm sorry for team on the network trying to mess us up today, but they failed. So basically we're just going to get straight ahead because of our time. So good. How was the last session? I want to believe you in the last session.
Yes, sir.
Okay. So what are the things you learned? Let's do a brief recap. Let's say for like 5 minutes. Just give me 2, 3 very striking things that you learned.
Okay. I learned about what an embedded system is, and also basic electronic terms and principles, like the resistor components, also like force, voltage, and current. What are the voltage, current, and resistance? What they are, and also the components of the electronics components.
Okay. So would it be cool and safe to assume that you and voltage are now friends? Like you understand it perfectly? You know how it gets our components fired up?
Yes, sir.
Okay, good. Don't mind me. I like interactive sessions, so I'm going to be making you talk. I won't say maybe talk a lot. So maybe you should get a pack of Tom Tom beside you or Baba Blue, whichever works fine. Okay, so we are going to be having interesting topics today. So basically, I'm going to pick it up from where we stopped. So we have looked at, I want to believe we looked at basic components, electronic components. We have looked at some. I have looked at, introduction to embedded systems. You have looked at capacitors, inductors, basically, all the very, very basic components that you get to see in any electronic circuits. So because we believe that when it comes, because you might be wondering why are we looking at those components when we actually are supposed to be talking about embedded systems. But mind you, embedded systems do not just work alone. You have to interface them to do, to execute exactly what you want done. So I don't want to go back to what we have done. So I'll just try and pick it up from there. Are you with me?
Yes, sir.
Okay, good. So if that be the case, we are going to be looking at a very, very interesting component today. And I repeat, very, very interesting component. You have it all over the place. It's very, very useful. And the limit of its use is hidden on the limit of our ideas. That means it's almost limitless. It's only our ideas and mind that can limit its use. It's called 555. Can you see my board? Can you? Hello?
I said I can only see some parts, like the upper part. I can't
Hello?
see. I am see, sir.
Now, what do we have?
I can see a little bit here.
You can see the upper parts, right?
Yes, sir.
You can see?
Yes, sir.
Can you see what's on the board?
I can only see 555 time. I didn't see the maybe R or the remaining part. I only see 555 time.
Yeah, timer, 555 timer. Okay, so this is what we'll be looking at. I'll try as much as possible to make it very legible so you can see and actually follow through. Okay.
Okay, sir.
But for you to understand the 5 timer, I will start with, I'm supposed to follow a sequence, so I'm supposed to look at integrated circuits. But let me start from ICs. You can see this, right?
Yes, sir.
Yeah. ICs, of course, you know what they mean. They are integrated circuits. Integrated circuit because you have some circuitry. From the word integrated, you should understand that we have some circuit inside of it. We have done analog electronics, basically. You have known how to, how some components work, your capacitors, your resistors, inductors, and basic components like that. But for this integrated circuit, we have circuits expected to perform certain functions inside of a certain chip. They are brought together because the whole essence of integrated circuit is, when you have circuits that use quite a lot, circuitry that use quite a lot, maybe you want to have achieve a delay in the circuit, or you want something to work as a counter, or you want something to work as something else, but that keeps cropping up, that keeps coming up. What we do, or what scientists do, or what producers or manufacturers of chips do, is to go on and put this circuitry into a chip. Mind you, if you're going to do it every now and then, it's going to become bigger because it's not going to be integrated. You're going to have to buy your resistors. You have to buy your capacitors. I hope you can see what I'm writing.
Okay, resistor, capacitors.
And then you have to, you are going to be needing transistors. By the time you start putting all of this together, you are going to be having a very big board. And these days, you know what we need. We are looking for compact designs. If I tell you, if you would want a Nokia 3310, I don't know if you know what that is. If you remember that phone, you would say no. The more we advance in technology, the slimmer our phones become. The slimmer or smaller our gadgets become. The laptops we get to see these days, very, very slim and beautiful. But that wasn't the case back then. Why do we have them slimmer, getting smaller and all? It's because of integrated circuits. There are circuits that by the time you start putting them together, it gets bigger, But we have dedicated chips that performs functions that that you would want to, then you take them one after the other and put them together. So one of such ICs is the 55 timer. So the 555 timer basically is very, very useful. And what it does, I can't even tell you what it does. It does a whole lot of things. It has a whole lot of applications. We have, I don't start mentioning the applications until we get started yet. So the 55 timer basically is a chip, an IC, and it has 8 terminals. Can you see what I'm writing? Hello?
Again, sir.
Can you see what I'm writing?
Yes, sir.
So let me just ask, have you ever used 55 timer?
I'm not using it before.
You have not? Okay. I think I would also have to be dropping chats because I really can't hear. Okay, so we have this, and inside of this, I don't want to go back because you can get it online, and I want to believe you have the outline for the course. So, so it is expected that we would have at least gone ahead of the class to do a bit of checkup on 55 timer. So you can actually see what we have here. I sent you a message. I would like you to can reply the chat. So looking at this, inside of this chip, very small, as small as it is, just for 8 pins, 4 on the left, 4 on the right. We have resistors, we have comparators, all of that. I don't want to. You have flip-flops, just one. You have flip-flop, you have output driver, you have transistors inside of this chip. All these things you have in the chip. We even have resistors, about 3 inside of it. If you are to replace them on a board, the board is going to become almost ×5 of the chip itself, minimum or more. So the beauty of ICs is that we have dedicated functions. You don't have to replicate them every now and then. It saves you space, it saves you time, and it saves you stress. So for the 55 timer, for me, I like practical. and I like us thinking wide. I like ideas. So I want us to dive right in and start. We don't have to go and talk about the structure, the three resistors inside, 35 this or that inside. These are things you can get online. But for me, I want us to be practical oriented. So when we talk a bit, then we start looking at applications and we start looking at ideas. Are we together?
Yeah.
Okay. For basically for the 5 timer, it can function in 3 modes. 3 modes. 1 is stable. 2 monostable. And then 3 is bistable. Can you see the board?
Yes, sir.
Okay. I dropped the chat. You are here to reply. Check the message section. Okay. What do you understand by Astable? Have you ever heard of it?
I had a so I really go in detail.
You really don't get, right? Okay.
Yes,
Astable means that, in digital electronics, we look at, how do I put it now? We look at, we say analog is, continuous, while digital is discrete. We are looking at levels. But basically, let us look at 1 and zeros. In digital electronics, we deal with 1 and zeros, even though we can have more. But let's just say we have 1 and zeros. And basically, what does 1 and 0 mean? Does it mean you write 1, you write 0? 1 and 0 is just typifying states that we can have. Where your 1 goes, your 1 would mean I. Let's say 1. Let me not get the board all modeled up. So we start with Astable. Astable just means that it has no stable state. Basically, like I was saying, we have 1 and zeros when we talk about digital electronics. But have you ever seen 1 inside any chip? No. Neither have you seen 0 in any chip. Basically, what we would have is 1 means high. And 0 means what? Low. Again, what does high mean? High means the highest point of your power rail, and low means the lowest point of your power rail. Basically, you're talking about what? 5 volts, and let's say 0 volts. This would mean for a 5 volt system, if it's 9 volts, this would mean 9 and 0. If it's 12, maybe 12 and 0. Of course, we can have intermediate levels, but for this purpose, we are looking at just 2. So your high means 5 volts, your low means what? 0 volts. That means your 1 means 5 volts, the 0 means 0 volts. Good. Let's go back to Astable. Astable, like I am trying to make you understand, means that the output of a 5 timer or the output of a system that is astable in nature has no permanent state. What do I mean? Of course, output is meant to be, high or low, maybe 5 or 0. If you want to power LED, for example, if you want to ask you to put on an LED, maybe if it is high, the LED will come on. Then if it is low, the LED will go off. So at a particular point in time, you should be able to say, okay, this thing is on. For example, the light in this place where I am is on, and that is the permanent state until I go put it off. So I can confidently say that the position of my light, of the bulb in this space, in this room where I am, is high because the light is on. But for Astable, you cannot say that. What do I mean? It's neither high nor low, because for a fixed period of time, it goes high. This is your 5 volts. Then suddenly it comes what? It comes low. This is 0 volts. Again, it goes up. You see 5 volts. This is the waveform. Then it comes low. That means 0 volts again. And that goes on for infinity. It goes on till infinity. It is high, it is low, it is high, it is low. So, Mr. Sorry, I didn't get your name. What's your name, please?
Astable.
Are you still there?
Yes, sir. Astable.
Adeboye. Is it Daddy Gio?
Yes, sir. Yes, sir.
You are Daddy Gio. Where do you, sir? So, I don't know if you get. So, if I ask you, what is the state of a system that has this kind of output? What would you say? Would you say it is high or would you say it is low?
No, sir. I can't say it's high or low.
You can't say?
I can't say it's whether maybe it's not high, then it's not low, because it's thinking like
Exactly, because it is fluctuating. It is not, you can't say the state is high or the state is low. It can be in any state. Because if you just wake up, let's say you are not, for example, let's say that is how the light here runs. And I come to pay you a visit. And somebody calls me, hello, Fash, the light in your house, now. Is it high, is it on, or is it off? I'll just tell you, my brother, I don't know. It can be on and it can be off. Any way you see, that's so it be. So that is how Astable is. It's neither high, you can't say. It can be high or it can be low. Don't mind you, what I'm talking about is the state. The permanent state is neither high nor low, meaning it has no permanent state. Are we together? So automatically, what comes to mind? If we pick it up from here, like I said, ideas is what I want to start talking about. What kind of system do you think would require this? Do you think this would work fine with the light bulb in your room?
No.
Mr. Adeboye, do you think so?
No, sir.
I can't hear you.
No, sir. No, sir.
It won't, because it's just like the light in the room does the video, and before you know, you want to spoil my eyes? You want to spoil my eyes? I beg, put off that light. But basically, this circuit, as useless or as irrelevant as it seems for your bedroom or for your sitting room, it is very, very useful for some other applications. Can you think of an application that uses something like this, Mr. Adeboye? Can you give me an example?
Though there are some lights, like some light that all this type of light that maybe at certain interval. I don't know, something like Christmas light that keeps turning on and off.
I knew it. You like Christmas lights. Mr. Adeboye likes Christmas lights. I knew you were going to mention Christmas lights. Yeah, and you like Lauren Abi. Hope you don't like manga as well. So yes, you are right. That is one application of this. Because of the effect, when it's festive time, you see light coming in and on. You see that jingle bell, you put light on your Christmas tree. Such a design is all we have. The state of the light is neither on nor off. The permanent state rather is neither on nor off. It can be on and off. So that is one application. So you have successfully said you have what? Christmas light. Are we together?
Yes, sir.
Now, can I have another one from you? Or should I shoot?
Yes, sir.
You said what?
You can. I can't think of another example now.
Ah, now I can't hear you again. Okay, let me just give one more example. My own example, let me just give you. How about okay. Can you see what's on the board?
Yes, sir.
Astable? Yeah. Siren or emergency light. When I say emergency light, you know now the ones you have on your police van. How do you think this light work? It is a system that works based on a stable output. You see it come on and off. For the lights, of course, on and off. Same thing applies to the sound. If you use to control your sound, of course, it is more than that. But you see, wow, 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 off, on, wow, something like that. That is another one. So, like I said, this sounds like maybe toys, but it is more than that. You might need. I will still take it because for me, like I said, I like very sweet and practical applications. So I'm going to mention two more. Have you ever thought of? Hello?
Sir, I'm hearing that. Hello, sir.
Okay. Have you ever thought of a very, very crude, or let me say the very first times we had traffic lights? What do you think the concept was as way back as then? It is unstable. If you give equal time to these people, that means when they sight, let me just say basic traffic light. Maybe for just 2 lanes or 1 lane, you pass, you stop. So while this is high, what would happen? A light, the other light will come on, and the other side will what? Will be off.
Yes, sir.
Cars will pass on this side, they will chill out on the other side. And when it is reversed, when this guy goes, I don't know if you understand what I'm saying. So these are concepts. These are what? Concepts. What else can you think of? For me, I can start to think of this as find an application for it when it comes. I hope you, as a guy, you like war fumes, right?
Yes, sir.
So you like war fumes, and basically, what if we use this to automate a gun, automate a particular weapon? The output will be unstable, and you connect it maybe to the trigger, so nothing is there. But what happens? Can you see my hand?
I can see your hand.
Can you see my finger?
Yes, sir. No, I can't see the other one. I can only
when it is high, the trigger is pulled. When it is low, it releases it.
Yes, sir.
Okay, it's just my hand. Like when it is high, it pulls the trigger. It is low,
okay,
it releases it. High, low, high, low, high, low. And the next thing is doom, 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 doom. You don't have to be there. Somebody will now come and say, I have this weapon, you know, the way they give me weapons name. This is AK-73. It is automatic. Just press the button and it starts shooting on its own. Automatic machine gun. Automatic this. And these are the kind of concepts. That's how people think. That's why I said that ideas. Who would believe that this same timer that you just said can be used for Christmas lights on the tree, jingle bell, and the zero for none. can also be used for very high-end, like high-end applications. What is going to be the difference? What will limit its usage, like I said, is what? How well we can think. Okay, let's move on. So how do we set this up? Let's move to go to the circuit diagram. Time is flying. And I want us to fly as well. But as you are flying, make sure you don't fall. I don't have first aid yet. So basically, the setup is like this.
I can't see the right hand side very well.
This side?
Yes, I can't see that side.
You can't see this side, have you?
Yes, sir.
How about now?
I can only see the left hand side. I can't see the right side. I can only see.
You can't see this side?
Yes, sir.
Can you see this side now?
I can see partially. It still remains small, like where the line is ending.
Is it better?
No, sir. The diagram is close to it, very close to the
Okay. Maybe I'll send it. Okay, let me just take you around. Can you see this point?
Yes, sir.
That's the ground, okay. Can you see this R1?
Yes, sir. I can see it, sir.
Okay. Can you see R2?
I can see R2, sir.
Can you see C1, capacitor 1?
Yes, sir. Yes, sir.
Can you see pin 7? 6?
Yes, sir. Yes, sir.
2?
Yes, sir.
1?
Yes.
5.
Yes.
C2.
Yes, sir.
Okay. Then this is 3. Pin 3 going to R3.
I can see R3. I can't see R3.
Then LED.
I can't see LED also,
Okay.
sir.
Can you see R3 now?
I can see the resistor there, but I can't see the label. I can see the resistor. I can see the resistor.
Okay. Let me put it here then. So can you see the rest? Can you see the one?
Yes, sir.
Okay. But basically, the most important thing to know here is the formula, so that you can put this up together. Your height and 4. The beautiful thing is it works fine on breadboard. We are getting there. We have your pin 8, we have your pin 4. You join it together this way, and 9 volts. You can get your 9 volts battery and plug it in. Can I clean?
Yes, sir.
And of course, you should be able to get this circuit online. What is? Let me see if I can write the formula here. The T. Let me write it out so I don't know those things up. So basically, one thing should be the question, or should be a question on your mind, which is time. How do I know for how long this will be on? For example, you want to go on ahead to design the, what's it called? The gun I just mentioned. Okay, is it very slow automatic gun you want to design? Like, pa, pa, or you want pa, 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 or you want, you know, that should be the question in your mind. Like, what I'm saying is, how do I design the timing? How do I calculate for the timing such that, notice when you look at waveforms, I want to believe about waveforms. This is the duration, right?
Yes.
If you want it to be very, very small, or you want it to be slow, something like that. Even if it's traffic lights, for how long do I want this side to wait? So how do you calculate the timing? This is the period from here to this point. This is half, and like that. So the formula is what I'll be writing on the board right away. We say T equals to 1.1 into bracket.
I can't see the upper part, sir.
Okay, I'll bring it low. Can you see it?
Yes, sir.
Okay, so this is how you calculate your time. T equals to 1.1 R1 plus R2 times C. Of course, your unit is going to be in seconds because you're talking of time. So that is for how long or how short it is going to stay in either of the states. So that's the basics.
Sir, I have a question.
Now, let's move on. Let's move on. quickly. But before I move on, of course, your first assignment is going to be to design. And by design, I mean I need the values of R1, R2, and C. You know, that would give me, okay, I will type it for you in the section. So that you can solve it. I'll type for you in the chat.
So the capacitor there, in the circuit you drew earlier, we have C1 and C2. But in the formula here, we have only one capacitor.
Okay, thank you for noticing. C1 is the one that is useful for our timing. C2 is actually not compulsory. It's just to provide stability for the circuitry. If you like, don't use C2. So it's not, in fact, you can even remove it, but it provides stability. So most times you can put a value for C2. You can put C2 equals to 10 nanofarad. It just provides stability. It's not part of, it doesn't matter. It's inconsequential.
Okay, sir.
It should still work without that. There may not be stable. So let me type your assignments right away for this particular one so that we can move on.
Right.
Okay, I've dropped it. So let's move on. You know, remember I said we have 3 modes. We'll be talking about 2. The next mode is what we call monostable.
I've not seen the question, sir. You
have not seen what?
The question.
Check the chat. Check the chats.
Last message I can see here. Have you ever used the
Can you see our chat?
I can see that one.
Can you see the chat for the meeting?
I can see the chat for the meeting. And what I have there is, have you
check,
ever used
I've dropped another one.
I can't. I've seen it now. I've seen it now, sir.
Check again. There are 2 chats there.
2. Okay, I've seen the design and
good.
automatic.
Okay, maybe there was a delay.
Okay, sir.
All right, good. So, can you see what's on the board?
Monostable, sir. Monostable.
Monostable. Yeah. So we are still looking at 5 timer. We have, when we started, we said it has 3 modes. We have the Astable, we have the monostable, we have the bistable. So we're looking at just 2 before we move on. The other one is going to be the bistable and the monostable. From the word mono, what is it telling you? It has one stable state. Yes. Remember, the Astable has no stable state. It is high, it is low, it is high, it is low. That's what the Rache calls Oshibalabala, something like that. But in the case of monostable, the guy is very gallant. It has a stable state. If you disturb it, let me use the word perturb. If you disturb it or you perturb it, it will do but it will still come back. I don't want to, sound like, if you give, for example, the stable state is, standing tall. Even if you give it punch and it does, and it go, sorry for that. So what I'm saying is that the state, it has a very stable state. If you perturb it, yes, it can go low, but it will come back and stay in that state. Such that if it is not disturbed, you can confidently say that my system is in this state. So we say that the state is like this. Let's say we are using high, it is high, like that. But if you disturb it, go low for a bit and remain high. Are we together?
Yes, sir.
So now it's looking like, what are we talking about? What is this? What do we do with this? It is staying high, you disturb it, can go low, but it will go back and stay there. What application can we find for this guy? In fact, there is one that I don't know if you would have noticed it. This is like what? It is useful, very, very useful for, let me say, delay systems. If you look at your, I don't know, for your stabilizer at home, you know, there's a function on stabilizers back then. One red button that you press, they say it is what? Delay. Are we together?
Yes, sir.
So this is how it works. Outputs like this, like that, are called monostable. It is on its own jelly, but then you look for its trouble, so that your stabilizer will not come on immediately. So by disturbing it, the stabilizer will now go low to supply outputs for this period of time.
Right.
This is what we usually calculate for. We should now go low. That means there will be no outputs. After the expression of this going low, it is now what? Will go up. It is now bounce back up and level back up to its normal state. It's not going to go back to the high. Let me say 5 volts. It's meant to be high, but you have looked for its trouble. It went low. You have perturbed it, or you have triggered it, whatever time it is you want to use. But after that short while, it will go back up and remain there. And that is why for your stabilizer, once you disturb it, you activate that your red button or whatever color it is, it goes low, it doesn't give you an output immediately. But after a while, what happens? It shoots back up and it supplies you your output, and you can begin to watch your TV and enjoy your Champions League final. Are we together?
Yes, sir.
So, can you give me an application that comes to mind? Think of something.
Oh, can
anything comes to your mind?
Can a switch be categorized into that school?
Come again.
A switch for light.
Can what?
I said, can it be categorized into that type of category?
Well, I don't know. This is not how switches work. Switches don't have this kind of. It's just like you telling me that if I press the switch in your sitting room, it goes off. Will it go back on its own? No.
Oh, I know, sir.
It will go back off only when you go and press it again. But this one, either you press it or once you disturb it and you go, itself will come back on without anybody touching it. It will always go back on its own to its normal state. If you have that kind of switch in your house, I won't come to your house. That means there is something in your house. I put on a light and I go. Before I get to the gate, the light don't on itself. Bros, you go stay in your house alone, no?
And okay, what about
so do you get the difference?
Alarm? Yes, I get the difference, sir. Yes, sir. And what about alarm circuits? Like, let's say it's initially to be off. Then unless it senses something, then it goes on.
Okay,
then
yeah, this would work for alarm circuits that goes off temporarily.
Yes, sir.
It now goes off on its own. Yeah, that would work for security systems, such that you don't want it to constitute a nuisance to the environment. I'm even coming to another thing. Then once it senses maybe an intrusion, it blows an alarm for a little period of time and keeps quiet. It doesn't have to blow alarm for a little period of time, maybe 10 seconds, 5 seconds, 2 seconds, and keeps quiet. Also, the output can also go on to trigger something else. Maybe a device that can send maybe SMS, maybe to the police, or alert yourself. Maybe it's your warehouse. Okay, let me keep quiet. So basically, like I said, ideas. It is beyond all of these theories and all. Your ideas is the only thing that can limit the application of all of this. So something like that is only what is a monostable. So such that after it sends the signal, after it sends the SMS, after it sounds that alarm on its own without anybody touching it, it go back to the quiet state, its normal state, and it stays there until something else looks for its trouble. That is another intruder. Are we clear?
Yes, sir.
So in this case, what is the circuitry? What does it look like? Well, similar to that other guy, but you know that this one, the Astable is it runs in perpetuity. How do I explain that? Once you connect it, since there's no stable state, it keeps going up and on, up and on. Nobody needs to touch it. 10 years from now, go back there, it's doing up, on, wing. But for the monostable, remember, it will stay as a gentle boy in its stable state unless you go and trigger it. Unless something happens. That's what they call it, trigger. Unless something happens that looks for its trouble, unless something happens that makes it change state. So that means you need a button. For example, look at this. Can you see the circuitry on the board?
Yes, sir.
Okay. So this is the trigger, like a switch. Or this is where the pulse. I don't want to confuse you. Maybe a pulse. When you press the switch like a pulse, it will go high and then go back low. This is where it will go in. And once this happens, you have to stop the what? The state. Then the monostable will change state from a stable state, go to its unstable state for the period of time that will be calculated. As usual, C2 is not compulsory. It is just to provide stability, and you can make it 10 nanofarad. Okay, are we together?
Yes, sir.
Okay, now you can draw on that circuit. Let me replace this for you. I just want to do practical so that you can have a signal that will trigger this for us. Can you see the board?
Yeah. I can see the board, sir. That you the down the D1 is a LED or normal.
You can see this part.
I can see this part, sir.
This one.
Is it LED,
LED
or normal DAB?
LED. So what will be the formula for this? Can I clean now?
Yes, sir.
So the formula for your monostable is T equals to 1.1 R1 C1. That's all. So this determines the time, the duration for which it goes low, like goes to its non-stable state, then before it returns back to its normal state. So the other one is bistable, which means it has what? What's the meaning of bistable?
It has two states.
I'm gonna give you an assignment for monostable. You think about it on your own. Can I hear this?
You can clean it, sir.
Can I?
Yes, sir. Yes, sir.
For your bistable, your bistable has two states. It has two stable states. Wow, that's sweet. It has two stable states. It can stay on your high state on your one for as long as possible, as you want it, or it's not disturbed, and it can stay on your low state for as long as possible, depending on you. That is your switch. You know, you talk about the switch in your house the other time. That's how that works. When you are going out in the morning, you put it off. Wow. That guy stays there until whenever you return. It can be 1 year, it can be 5 years. When you return, you are going to meet it what? Off, unless anything else, unless you're not the only one at home. So, the same way, when you get back home and you do what? You put it on and you go to bed. Provided NEPA don't take light, it's going to remain on till whenever, maybe till you wake up or decide to put it off. So, those kind of applications are what we call bistable. Any of the state is cool for it, it will remain stable unless you can change it. You change it, it stays high like forever. You change the state again, it stays in the other state like forever. So that is that for the 3 modes. So let's fly. I won't say anything and draw second about that. Follow from there. So are we still together?
Yes, sir.
Okay. Have you ever used the breadboard?
I've used a breadboard, sir.
So have you ever used variable board?
Yes, sir.
Okay, good. So I'll just talk about those ones briefly, since we have used those. Then when you want to put circuits together, for example, I don't want to put, let's say prototyping for the very basic prototyping. You have an idea. You have designed the automatic machine gun control, and you want to be sure that it would work. You have done it on paper, you have calculated the time. Okay, it should take 10 seconds. Okay, R1 should be 3, R2 should be 4 kilo ohms. You have done all of that. But mind you, that's on paper. But now you want to show someone that this actually works. Or you want to show to yourself that, or convince yourself that this should work. It should be a perfect time. You should do this or you should do that. This circuitry should perform its design, you know, its function as designed. What do? You have to buy the components and make one first. Put the components together, or let me say, put the design together. So you get the components, you get your capacitors, you get your resistors, whatever it is you have in your design, and you put them together. You put them. How do you put them together? That's where we have your prototype boards, you have your breadboard, you have your strip board, you have your yellow board, they call it line board, line or dots. So since you know how to use those, so I think we just keep it all together. I believe, yeah, just you in the class. So yeah, we'll skip that all together. So, but basically as a work of that, although there's some circuits that we cannot even try to do on breadboard, it will not even work, particularly high frequency circuits, but we're not talking about that. That's higher than basics. So we'll just move on. And then I want to believe you have seen schematics. Most times when you go online, you see circuit diagrams. Am I right?
Yes, sir.
You see circuit diagram, and we call them schematics. You see your capacitor joining one resistor, joining one this, joining one that. Those are schematics. And basically, you have to know how to read the schematics. They provide a guide to us. They provide a guide as to how the components are connected. Not essentially how they are arranged on the board. Not essentially how they come maybe in your circuit. No, it just shows you what is connected to what. It's not that when you open a circuit, okay, I'll first of all say the resistor, and I'll say capacitor. No, it only shows you two things: how the components are interconnected, and also tells you a guide of how your electrons, or let's say currents, travel in the circuit. Basically, that's why we have schematics. Of course, schematics, which means give you an idea of how things are pieced together. So a quick one. I know most of you know about schematics. Let me just draw. Let me see what do I draw. Okay. Okay, for example, let's say you have a circuit like this. Hope you can see what's on the board.
I can see what is on the board, sir.
Can you, Mr. Adeboye?
Yes, sir.
Okay. So this like a schematic. Basically, this is just telling us that, okay, I'm not going to explain circuit, it's just a draft. It's not like anything. It's not what we're looking at. It's just telling us that, okay, these guys are connected in this particular way. It's just telling us that, okay, this design, you can tell the number of components. That's one of the benefits or relevance of schematics. It tells you, gives you an idea of the number of components you have. For example, if you have a design, maybe in your head, you quickly piece this together, you pen it down. This is going to tell you that, okay, I'll be needing 1, 2, 3, 4 resistors. It helps you do a component count as quick as possible. And that also gives you an idea of how much you'll be spending. For example, component count, 1, 2, 3. Okay, 3 resistors. Beautiful. I'll be needing 1 op-amp. Okay, I'll be needing what else? Reference voltage. After you get that, okay, 1 resistor. You can have a component count, and that will help you in planning. That's one. One thing schematic does for us. Another thing is that it helps you have an idea. Okay, this is coming this way. This connects to this, connects to that. Okay, are you sure to connect to this? It helps you visualize your concepts. It helps you put your concept, your ideas on the board so you can now analyze it yourself. Oh, this is not here. No, this should be here. This should not be here. And also helps you track, how electrons travel, or let's say current travels in the system. So that's why we have schematics. It doesn't mean that when you open your board, let's say I'm not saying that is it though. Let's say it's what you have in your mobile phone. It doesn't matter. By the time you open your mobile phone, the first thing you see is wire one, followed by arrow two. No. You may even see wire first. You may even see the dial LED first. It's just telling you that these are the things you have in circuit, and this is how they are connected, not how they appear. Are we together?
Yes, sir.
Are you saying something?
No, sir.
Mr. Adeboye.
Sir?
Can I claim?
Sir, that place you have a minus. Is it 5 volts you wrote there that is connected
Can I
to that
claim?
minus side? You can clean, but before you clean, sir, at that minus inside the IC part, is it 5 volts connected to the minus?
Yes, it's not reference.
Okay.
Yes. Yes, 5 volts.
Okay, sir. I can clean it, sir.
Okay, can I clean now?
Yes, sir.
So let's look at transistors. Did you do transistor in the other in the first session, last session you had? Did you touch transistors at all?
We just made mention of it as an electronic component, so we didn't explain in details.
Okay. So what do you know about transistors, Mr. Astable?
Transistors are a semiconductor device for switching, and it's three terminals. So, and it's three terminals, and we have maybe either the NPN or PNP. That side, we have bipolar junction transistor FET.
Is that all you know about transistors?
Yes, sir. And I don't want to go.
Okay.
What I really know more of theory.
Have you ever used any?
Yes, sir.
Okay. All right, let's shoot. For transistors, basically, transistors are three-terminal devices. Three-terminal devices, although there are some that you get to see just two terminals. Those are special cases. Maybe it is light dependent, but I don't want to go into that. Let's look at the fundamentals. You are right, three-terminal devices. You are right, they are semiconductor devices. Good. But let's look at it from a more practical angle. I know you have done a lot of theories in school. So let's try and be a bit more practical. Can we?
Yes, sir.
Okay. So transistors are devices that, they are more like, I don't want to use amplifiers, but basically they're like amplifiers. They take in, how do I put it now? But before we go on, let's look at the two types of transistors we have. Basically, we have BJTs and also we have MOSFETs. What is BJT?
Bipolar junction transistor.
Beautiful. How about MOSFET?
Metal oxide semiconductor field effect transistor.
Field effect transistors. Okay. Now that it is obvious you were at the naming ceremony of the transistors, we'll move on. For the BJTs, we have two types. We have the father and mother. We have the PNP. And we have the what? NPN. I don't know how deep we'll go, but let me pick one and explain.
Yes, sir.
The most popular, the most common of these two is the NPN. So let's talk about NPN. But first off, for your PNP, you have this. This is your collector. This is your emitter. This is your base. All right. This is your NPN. The arrow here shows you direction of current flow. So for your PNP, current flows outward your emitter. While for PNP flows into the emitter. Okay. Quickly, let's now jump into some practical stuff and stop talking so much of theories. Okay, for our NPN, this is what we have. We have this. So this represents our terminals, the terminals of the NPN transistor, base, collector, and of course the emitter. However, the way this guy works, BJT transistor, the way they work is this. Mr. Adiboye, I don't know if you were around sometimes back, some years back, or I don't even know if you were actively involved or you participated in this scheme called Ponzi, MMM. Confess, were you there? Did you participate?
And I heard about it, but I didn't participate.
Are you sure you did not put your school fees inside?
Sir, I was honest.
Okay. So do you know how it worked?
And it's like someone put money, and the money the person put is used to pay. And let's say you refer someone, so the person you refer, the money they are paying is the money they are using to pay another person.
You are even explaining how it crashes. Tell me about the basics. If you want to market to me, is that how you market it? You are not a good marketer. Thank God your field is electronics. Okay, that's on a lighter note. But basically, the way this what is it called? The MMM or Ponzi works is that an amount of money. You are promised a bigger sum of money, a bigger percentage of the money as interest. For example, if you put in 5 naira, MMM says that they will give you 30% extra. 30% of whatever it is you put inside. Let's use 100 so we can understand better. MMM will tell you that if you put in 100 naira, at the end of the month, they will give you what? 30% of your money as interest. How much would that be at the end of the month?
$130, sir.
I know you like money. You understand that one. 130. Okay. You get 130. Wow. Somebody's excited. 100 naira, I'll get 130. Wow, 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 wow. But the question people did not ask, or people failed to ask, is the 30 naira, the 30%, where is it going to be coming from? Anyways, I'm not a Ponzi marketer, so let's come back to class and talk about electronics. In our electronics, I can tell you in a way that our transistor works like an electronic Ponzi. Are we together? It works like an electronic Ponzi, particularly our BJTs. It takes in current, and we are looking at NPN, don't forget. It takes in, or it allows, we are saying the same thing, it allows a particular current, small amount of current, to go in through the base, and then it allows a larger proportion of current to flow out through the what? Emitter. Remember Ponzi? You put in 100 here. What comes out here? 130. But this time around, there is something that determines how large your interest will be, how large the output will be. It is called beta. Internally, we call it beta. So typically, we have beta of 100, 150. So let's say beta is 150. What is this telling us? That whatever it is passed into the base, the electronic Ponzi guy, your NPN transistor, is going to do what? Multiply it by what? 150 and give it to your what? Emitter. So meaning that if we have 1 milliamp here at the input, as at the base, what would come from, what will flow out of your emitter is what? Remember, what will flow out? Can you remember the formula?
Take the formula for calculating emitter. That is
T equals to what? Beta IB. Can you remember?
Yes, sir. Yes, sir.
And also, we have that your E is approximately equals to your what? C. Yes or no?
Yes, sir.
So that means it is safe to assume or to write that your E is approximately equals to what? Beta I B. You can see it, right?
I can see it, sir.
So, like I said, it is safe to assume that your E is now approximately equals to what? Beta I B. Are we together?
Yes, sir.
So, if I put in 1 milliamp here, what's going to be the emitter? Putting in 1 milliamp, your emitter is going to be what? Beta of 150 times 1 milliamp. What do we have?
150 milliamps.
So we're going to have 150 milliamps, right?
Yes, sir.
So would you agree with me? Was I right? Was I correct that our NPN transistor works like an electronic Ponzi scheme?
You're right, sir.
Okay, well in this case, this guy is not robbing Peter to pay Paul. The extra, the extra for in this case 149, the extra is going to give you is going to come from here. Can you see the direction? This arrow shows the direction of current flow. It's going to come from the power supply, VC. So this guy, your B, let's look at it in another way. Let's not look at it as a Ponzi. Your base acts like a bouncer. The bouncer is at the door. It opens the gate for people to come in. So let's say you want to come in, or people are crowded at the entrance of a particular hall or a particular place. Maybe they want to go and see P Square. Who is running now? Who is trending? I don't know. Whatever it is, they shall want to go and see an artist, and they are right there trying to rush in. If the bouncer flings the gate wide open, what happens? Everybody rushes in. That is your base. Your base determines the current flow at what? At your collector or emitter. And if you close the gate so tightly, you are holding it, you open it a bit, one person comes in, you shut it, one person says, now only 8 first go inside. You are controlling current. People will not rush in. You are controlling the rush of people. That is how the base operates. And mind you, for every little opening, the beta is out of him. Mr. Deboye, are you here?
Yes, sir.
Or you have gone for Holy Ghost Congress?
No, sir. No, thank you.
Okay, so this is how this works. I don't know if I should take you towards design for this. Let's see. Do I have time for that? So basically, that's how it works. We'll skip. So this is how your, what's it called? NPN BJT works. Current comes in, an amplified version of that current comes out. So meaning that if the current is like this, what we're going to come out here is something larger, with larger swing, like that. We'll leave it that way. Can I clean up the board?
Yeah, you can finish.
Or should we look at a particular circuit?
Let's look at the circuit.
Or you have an idea you want to share with us?
No, sir.
Do you have a rechargeable lamp at home?
Yes, sir.
You don't?
I have, sir.
Okay, so let's try and design one. Or you think they don't design it? They just put it together?
I need to design it.
Okay, let's quickly look at something elementary. Let's look at LED design. Okay, are you there?
Yes, sir.
So let's say the specification of this LED. After ordering from China, I know you guys do that a lot. After going to AliExpress or going to wherever it is you go to, you order LED from China, and you look at the pack, you look at the power rating, you look at the specifications, and see that it is what 3 volts, 1 amp, for example. That's 3 watts. But you want to control it. You want to limit the current. You want to allow maximum current. You want to reduce maximum current. What do you do? But Mr. Astable, first thing first, if I tell you that this device, okay, I didn't give it banter already. Okay, let's go on. But from what I explained just now, for this device to come fully on, to have 3 volts and to have 1 amp, what does that imply? Can you tell me anything? What is that telling you, circuit-wise?
Okay, that let LED be the 3 volts to 1 amp.
It is what?
I can't get the question, sir. I can't get the question.
Okay. I said for this LED to have 1 amp flowing through it, what does it mean for the transistor?
That the transistor it will amplify the current it will supply the available current. Even the current from the
Okay. Your answer shows you that you like theory so much. I expect practical answers, responses. That means that IC equals to 1 amp. Do you agree?
Yes, sir. Yes, sir. Okay, there
Because
current.
it is in series and it is coming this way. And also, it means that your IE is approximately equals to 1 amp. So the question now is, but are we sure this is going to happen? On what condition would this happen? On what condition would this happen? It's on the condition that RB, the IB, the current flowing to the base allows this. Remember, IC is an amplification of what? IB. If IB is too low, no matter how you amplify it, it will not suffice. Like our other example, if I allow 1 milliamp to go in here, what are we going to have at the output? 150 milliamp.
Yes, sir.
Is it enough for the LED?
No, sir.
No. So what do we do? And we move backwards. In design, you move backwards. When you're analyzing somebody else's design in class, you are doing assignments, you move from here to here. But when you have your own design, you move from here to here. So now we have to know the amount. We have to know the size of IB that we need to guarantee us 1 amp. What do we do? Astable.
We calculate the IB that we needed. This from the formula.
Beautiful. So what would that give us?
So that is IB. That is IC over beta. 1 over 1.
Okay. What's that? Point in that for me, please.
Okay. Yeah, coming, sir. That is 1 divided by 0.05. That is 66.67 amps. Milliamps. All right. Okay, oh, sorry. I'm coming. That is 0.0066. That is 66.67 milliamps.
So, what is that?
67 milliamps.
Okay. Are you sure it's 67?
Yes, yes, sir. It's approximately 67.
I disagree.
Wait, okay, sorry, sir. That 150 is in milliamps.
It's not 67, it's 6.7.
Okay. 6.7.
Mr. Astable, are you trying to embezzle the remaining?
No, sir. I forgot that the 150 is in milliamps.
Okay, so now you have an idea of what? Of what your IP would what? Be.
Yes,
Moving forward, we now have to know the value of what? RB. Are we together?
yes, sir.
I remember that formula they gave you in school and you wrote it down quickly without asking why. When they told you that IB equals to VCC minus VBE, can you remember? Over what? Can you remember you wrote this one down very quickly without asking?
We didn't ask the reason, just wrote them down, like based on the calculation of the transistor. How to calculate.
We're just writing it. Equation 1, used to write equation 1. The next one, equation 2, we're just writing it as well. That's good, not bad. So now we have to calculate for RB. We have IB, we have VBE, we have VCC. This is the only guy missing in action. So how do we calculate this guy? Your RB will then be VCC minus VBE over what? IB. And that will give you what? 3 minus 0.7 over what? 6.7 times 1000 equals to what? 2.3.
Okay.
What's the answer?
3 minus. I'm trying to. I'm sir. 3 minus 0.7. Okay. 0.343, sir.
0.343 kilo ohms.
Ohm.
So let's take it back. Are you there?
Yes, sir. Was the network? I think it was network.
Yeah.
Yes, sir.
Do you know where this 1,000 came from?
This one, sir.
This 1,000 naira. This 1,000. Do you know where it came from?
Because the current was in milliamps, so the one over that 10 raised by minus 3. That is the one.
Okay. So that means your RP is what? 343 ohms. So that means you have to go to the market, you go and buy what? The resistor. Are we together?
Yes, sir.
So can I clean this part?
You can finish, sir.
Hello?
Yes, I'm here.
Can you hear me?
Yes, sir.
Okay. So, where were we? I was asking if I could clean this part.
Again? Yes, sir.
Okay. So, I said that means the value of base resistor is what?
343 ohms.
Okay, well, basically, you know that some, what's it called? Like the rechargeable I have, the way it works is that I can do what? I can vary it, I can make it dim, all right? I can make it bright. So if you want to do that, it's very, very simple. What do? You just take this guy and replace it with what?
Variable resistor.
Variable resistor. Beautiful. Whose maximum value will be what?
Maximum value will be 343.
No.
Oh, now this
Minimum value.
2.1.
That's minimum value. Then the maximum value can be something higher. It can be 1K. 1K is enough, or 2K, or 5K. So can get a 5K variable resistor. Then this will not be 5K. Such that you can do what? You can vary the guide. Are we together?
Yes, sir.
So although it's more than that, so you can see. And then what will the switch be? Because this is going to be forever on. Then the switch cannot be where? Yeah.
Yes, sir.
Anyways, let's sit down. So let's move on. That's just some design concepts. Are you sure that's all for the design?
What is it, sir?
Are you sure that's all for the design?
Yeah, for rechargeable lamp.
Yes.
Do have a circuit that charges the battery.
Okay. Anyways, let's move on. Let's move on. Because of our time, I think I'll just have to jump to, let's say, the last one we have for today. Let's look at where's the guy? We'll be looking at. Let's do H bridge. Then we'll move on. Have you ever heard of H bridge?
No, sir.
Okay. This is not your third mainland bridge. Neither is this the second Niger bridge. It is an electronic bridge. And the reason we need it, you'll see very, very soon. Okay, H bridge. Let me clean this up. So remember that when we talk about embedded systems, although we have been talking somewhat like about electronics sense, but embedded systems requires we talk about electronics as well. Reason being that after you might have done your coding, written your codes and all of that, you need to interface. You need to interface things to things. You need to interface your system, your program, your chip to some other parts. For example, if you want, okay, like we talked about siren earlier on, and we said the emergency light or siren, that what's it called now? For your monostable, it can come from, okay, let me not make it complex for you. So, for example, you want to control your motor, your pumping machine at home, or your electric motors that you know they work. How do they work? They can roll this way or they can roll that way. Or you want to make a toy car that can move in two directions. It can move to the left, it can move to the right. Or let's say, let me know left and right. Let me say back and forward, like forward and reverse. It can move to and it can move through. That's telling you that we have two directions. Are you together, Mr. Deboye?
Yes, sir.
Okay, that is why we need H bridge. You will soon see why. Let's look at this. H bridge is put together using 4 transistors. Transistor number 1, the guy is here. Transistor number 2. Transistor number 3. Transistor number 4. Pardon my drawing. And you see it's looking like H already. Yes, and then you have an electric motor here. Now, follow me. Remember, how does this guy work?
Okay, we supply current to the base. Then take this transistor.
Allow IV to go in. It gives you what? Astable.
That the network was crashing, so I can't hear you properly.
If you supply current to the base, what would happen?
And the current will be amplified at the emitter.
Okay. If you supply nothing to the base, what would happen?
There will be no current supplied to the.
So, looking at this, there is no current at the base. What's going to happen here? No current supply. Are we together?
Yes, sir.
So the way this operates is to open 2 alternate transistors at the same time. Remember your alternate angle, right? To open 2 alternate transistors at the same time. Let's go. If I put in a base current here, IB, I put in a base current here, IB, what happens?
Current will be supplied at the emitter.
Begin to flow. It comes this way, but it cannot go down here. Why? The gate here has not been what? Opened.
Yes, sir.
All right?
Yes, sir.
But then it goes in here, it goes through the electric motor in this direction, comes here. But remember, what's going on here? IB is flowing here, the gate here has been what? Opened. So the current now goes in this way and goes towards ground. So there's a complete packed flow for the current, isn't it?
Yes, sir.
From this way through the electric motor to this way. Then what happens to the electric motor? It will rev, it will roll because current has passed through it. Conversely, or alternately, if we now close these guys, but we open this other guy, IB and IB, what would happen? Current this way, but this time around, it will flow through the electric motor in the opposite direction and come this way. What happens to the electric motor? It changes direction. That becomes your reverse. And it moves backward and it keeps rolling. So this is why we say this guy is our H bridge. Before, this was a challenge. Imagine you just having power supply here and you connect to your electric motor. Can you change the direction of the electric motor without touching it? You have to come and physically remove wire here, remove wire here. So it was a challenge. So, but this guy helps us. This H bridge helps us do what? You know,
change direction.
Change direction, and that's why we call it H bridge. However, this H bridge is very useful. Its usefulness and relevance goes beyond toy cars or moving motors, like I just said. In your inverters at home. Anyways, in your inverters and some other things, this H bridge is there. Imagine, how does your alternating circuit work? This is how it works. You have this is still DC, this and VCC and ground. But by the time you put in your transformer here, what happens? And you start putting control circuitry. You on this, you off it, you on this, you off this. What happens to your transformer here? It starts seeing it as a what? Sinusoidal circle. AC. It goes this way, change direction, and we set it that way. But let me even ask you, what kind of circuitry would do this changing for you? Change this, of this, change this, of this, change this, of this, change this. What kind of circuitry? You have done it today. You are stable.
Astable, yes, sir.
On, off, on, forever like that. It does that. And what happens to your transformer? Let's say this transformer you have here. This is how we draw it. Now what happens? It comes here, induction takes place here, then we have a what? House fuse.
Yes, sir.
And then you connect your phone to it and start charging. And start telling, yeah, what charge you? Want to turn inverter? But basically, that we were able to do that because of what? Age bridge. So that's why we call this guy age bridge. So what we have to do is to factor or think of how to control the basis. So that's what we have for age bridge. So you can read up about your age bridge.
Sir?
But, you can read up. I don't want to go too deep into it. So I guess you would have to do some read ups. I would ask questions when next we meet.
Yes, sir.
So I think we have spent over 2 hours. Am I right?
Yes, sir.
Okay. So can we call it a day?
No problem, sir.
All right. But before we call it a day, let me quickly chip this in. For your MOSFET, how does it work? MOSFET is pretty simple. Let me just draw a quick sketch here. I can't remember the schematic basically. We have this, it comes down here. The only difference between your MOSFET and your BJT is that the basic difference is that what? Your MOSFET is voltage controlled. Are we together?
Yes, sir.
Remember what I said about your BJT? That when IB goes in, a larger current flows in your collector. All right?
Yes, sir.
But in this case, this drain source, in this case, it is not when current does not flow in. It is voltage. Once you apply a voltage to the gate, what happens? Current flows from drain to source. That's why they call it IDS, because it flows from drain to source. All right? So you apply a voltage, current flow. They call it transconductance because you are moving from current. Current is controlling voltage. But for BJT, current is controlling current. Are we together? But essentially, they work the same way. Voltage, your gate acts as your base, your drain like your what? Collector. Your source like your what? Emitter. Remember, for your NPN, your BJT, the more the base current, the more the current, your IC and your IE. In this case, the more the voltage, the more your what? Drain current. All right. So that will be all.
Okay, sir.
Did you enjoy the class?
Sir, what do you say?
Did you enjoy the class?
Yes, sir. Thank you very much, sir.
Okay. So see you soon.
Yes, sir.